Time series analysis. The file for this section is time series delegates.xlsx with me, Duncan Williamson. Techniques for working with time series in models that allow automated data generation and summarisation at any level. A time series is a set of measures of a variable that are ordered through time. Time series analysis attempts to detect and understand regularity in the fluctuation of data over time. Regular movement of time series data may result from a tendency to increase or decrease through time, trend, or from a tendency to follow some cyclical pattern through time, seasonality, or cyclical variation. Forecasting is the extrapolation of series values beyond the region of the estimation data. A regular variation of a time series can be forecast, while random variation cannot. In this presentation, we're concerned with analysing the independent x variable of time and the dependent y variable of something else, of something of interest. Notice, time is always the x variable and the y variable is the something else. Here are examples of time series, two completely unrelated sets of data shown in time series form. The sales of Amazon.com on the right-hand side from its beginning to the end of 2014. And the millions of air miles flown in the USA from 1996 to 2003. How would you describe the air miles data set? From the graph we can see at least two patterns. Until the latter part of 2001 we can see seasonality more travel at some times of the year than others. An overall upward trend until the latter part of 2001. So what happened after late 2001 might even be considered a separate series. It's certainly been reset to some extent. Amazon.com, their data are very similar to air miles in that there is a seasonality in their data and there is an upward trend to the entire series. The major difference between the two is that the overall trend of air miles are somewhat linear, whereas the overall trend of Amazon.com is curvilinear. Linearity or a lack of it is an important factor in time series analysis. In simple situations, data observations may be described by a straight line. A simple linear regression equation is fit to the data by least squares. A straight line model to account for a trend is in the form y equals a plus bx plus e, where a is the intercept, b is the slope, and e is the error term. Consider the example on the next slide, on the lone linear tab. Notice I've used year numbers and not the year values because year values can cause problems when creating the forecast. In this case, y equals 696.8929 plus 108.1905x plus e. If you change year 1 to year 9 in cell D5, that will give you the forecast for 2016 of $1679.61. And this is an example of an additive model. The completed graph, including the regression equation, is on the right, and whilst the R-squared value is very high at 0.9853, there's a hint, when we compare the actual with the regression line, that the data might actually be non-linear. Let's try fitting an exponential curve then, a multiplicative model. Right-click on the trend line and format it by changing it from linear to exponential, and you should get the new graph on the right. The new regression equation is y equals 765.84 times e to the power of 0.0926 times x. The lone EXP tab shows the new forecast amounts. Take some time to study them. And do look at the supporting regression statistics too. And notice that the exponential regression equation is significantly different from the linear model. The R-squared value is higher and the MSE value, the mean squared errors value, has fallen dramatically, which shows that there is much less variation in our estimates now. Index linear and index EXP tabs now, and on those tabs I've set out some new data for you. It's index numbers of industrial metals for 9 years. So complete the table in the range A4 to G12, complete the regression statistics section, and add the appropriate trend line to the graphs. Monthly time series observations very often display seasonal variation. The seasonal variation follows a complete cycle throughout a whole year, with the same general pattern repeating itself year after year. Obvious examples of such variation are things like sales of seasonal items such as suntan oil, We expect that sales of suntan oil will be very high during the summer months. We expect sales to taper off during the onset of autumn and to decline drastically in winter, with another peak during the winter holiday season when many people travel to sunny places on their holiday. Then increase again as spring progresses into summer, with the pattern repeating itself the following year. In addition to a linear or curvilinear trend and seasonality, a time series may exhibit cyclical variation, where the period isn't 1 year. In the context of business and economics, cyclical behaviour is often referred to as the business cycle. The business cycle is marked by troughs and peaks of business activity in a cycle that can last several years. The cycle is often of irregular, unpredictable pattern, and the period may be anything from 2 to 15 years and may change within the same time series. Here's some hypothetical sales of suntan oil, where we can see winter holiday with small peaks, summer holidays with large peaks, and the overall linear trend of increase in sales year by year. A second example would be gross earnings, annual gross earnings, year against earnings. A third example would be year and passengers, the monthly number of airline passengers. We're concerned now with analysing the elements of a forecast, that's taking apart the data, to see what it's made up of. Statisticians call this decomposition, decomposing or taking apart. On the next slide you'll see the elements of data series and how they are then said to decompose. So types of variation are trend, seasonal, cyclical, and random or irregular. We call this term the error term, or E before. A moving average of a time series is an average of a fixed number of observations that moves as we progress down the series. The Move Av1 tab show the formulas you need for a 5-period moving average, 5MA. And you can see them then in row 3, 4 through to row 12 in that third column, the 5-period moving average. So the moving average is smoother, i.e. flatter, that's the orange line. It's shorter, it's cut off at both ends. It's deseasonalized in that it removes the seasonal and the irregular components. That means it leaves the trend and the cyclical components. To create the ratio to moving average figures in column E, do the following. Enter equals average B4, B7 in cell C6, fill down to C18. Enter average C6, C7 in cell D6 and fill down to D17. Enter B6 divided by D6 times 100 in cell E6. Allows us to calculate the seasonal indices at the bottom line of this table. The spreadsheet shows you how I did that. The only thing that might be a little bit peculiar is the sum of averages being 400.1. We need that to be 400. So the seasonal index factor of 400 divided by R11, 0.9997, gives us a factor to deflate or inflate the averages by, to give us the final figures of seasonal index of 110.14, 97.45, 91.29 and 101.12. We then deseasonalize the series by applying those seasonal indices, which you can see in that third column, S, 110.14 is in 2012 W winter. You see it again in 2013 W winter, and again in 2014 W winter, and so on, the same with each of them. And when you divide sales, actual sales, by the seasonal index, it gives you the deseasonalized series Z divided by S, multiplied by 100. We find the trend in this way equals slope E5, E20, comma, B5, B20, known Y, known X, intercept E5, E20, B5, B20, which gives Y equals 152.8193 minus 0.8214x. We could add plus E, which we then evaluate in column F, the trend or prediction. At this stage then, we've decomposed S, T, and C is the final element to identify, the cyclical series. We find the cyclical component of the series by dividing the moving average series by the trend. To do that, we first have to estimate the trend, which is the function of the deseasonalized series versus quarter number. The function you get is 152.8193 minus 0.8214x, as we've just seen, and see the cells O18 to P18 for that. Use the function then to populate the trend prediction column. And now we've decomposed all three elements, S and T and C. You can see in the graph and you can see in the table. The cyclical component is found by dividing the deseasonal series trend value for the period and multiplying by the answer by 100. Taking quarter one, what we have is 170 minus the sum of 15.65 plus 2.35 plus 1.0155 plus E. There are problems in dealing with the cycle. Unlike the seasonal component, which is fairly regular, the cyclical component of the time series may not have a dependable cycle at all. Both the amplitude and the cycle peak-to-peak distance may be erratic, and it may be very difficult, if not impossible, to predict. Thus, forecasting future series observations can be difficult. One method that's often useful in forecasting time series is exponential smoothing. Simple exponential smoothing is a useful method for forecasting time series that have no pronounced trend or seasonality. And the concept is an extension of the idea of a moving average. Look at the moving average graphs now and notice how the moving average smooths the original series of its sharp variation. And the idea of exponential smoothing is to smooth the original series the way the moving average does, and we want to allow the more recent values of the series to have greater influence on the forecast for future values than the more distant observations. Exponential smoothing is a forecasting method in which the forecast is based on a weighted average of current and past series values. The largest weight is given to the present observation, less weight to the immediately preceding observation, and even less weight to the observation before that. The weights decline geometrically as we go back in time. We define a weighting factor W as a selected number between 0 and 1. Once we select W, for example, W equals 0.4, we define the forecast equation, which is next forecast times W, brackets present value, present actual value, bracket, plus, bracket 1 times W bracket, times present forecast. Look at the Exp Smooth tab to see the worked example. The model starts in C7 with this formula, which is exactly what we just said it should be. Drag that formula down from C7 to C21, and that's our forecast complete for a value of W of 0.4. In column D, I've created another forecast with W equals 0.8, just for comparison. We don't normally do two at once. Plot the actual and two forecasts on a graph to see how W equals 0.4 and W equals 0.8 differ, and there you can see. 0.4 is orange, 0.8 is purple. The actual is blue. In columns L to N, I've set up the MAE, MAPE and MSE cells to provide supporting data to assist with evaluating our model. MAE is the mean absolute error, the average absolute error. MAPE is the mean absolute percentage error, and MSE is the mean squared error. The lower the error values, the better the model. We can use GoalSeek or Solver to help us to optimize a model. We can optimize by looking to minimize MAPE or MSE. GoalSeek, data, what if analysis, GoalSeek. Minimizing MAPE gives the answer of 0.933334. Minimizing MSE gives the answer of 1.000095. If we use Solver, data, what if analysis, Solver, MAPE gives the answer of W equals 0.933334, the same, and MSE gives the answer of 1.000095, again the same. We've already used some of Excel's forecasting functions when we use ordinary least squares, the toolpack. The toolpack also has utilities for moving averages and exponential smoothing, and you should apply them to the examples we've worked through. Unusually for the toolpack, the results it gives here are volatile, which means that if you change the data, the answers will be updated to reflect the changes. Copy the Move Av to A tab and delete everything except columns A and B and C. Invoke the toolpack moving average utility and complete the dialog box you see there, and this is what Excel produces. You can see it's not attractive, but we can beautify it. And do take a look at the output cells to see the formulas, including column F that includes the standard errors. I've highlighted the SE formula that Excel has generated, the standard error formula. Copy the EXP Smooth tab and delete everything except columns A and B. Invoke the toolpack, exponential smoothing utility. Very similar to the moving average dialog box, as you can see there. Again, the outputs are not so attractive. We can improve on them. And here is my final version. Again, I've highlighted the formula in E10 for the standard errors. Well, that concludes time series analysis for the moment. Thank you. With me, Duncan Williamson.